Hello my friends, this is lecture 7 about calculating electric potential due to a point charge mainly and relating electric potential and electric field. That's the main learning goal for this. How do we calculate electric potential of a point charge or a collection of point charges? We learned that the potential can be expressed as electric potential energy divided by the charge. We can use this with a symbolic setup. We have charge Q here. It will have its electric potential around. If we bring another charge Q prime close by it, we'll do a work. That work will be an electric potential energy. We can calculate the electric potential energy actually using this equation here. Keep that in mind. Don't worry about this one here. This is simply K. So it's the same equation. K, Q, Q prime over R at our distance away. We will have the charge Q prime will have this electric potential energy. And we know if we divide electric potential energy by Q prime, we'll get to the electric potential due to charge Q over here. And we can easily see that this will give us this equation here. Again, don't worry about this. If you're reading the book, you will see it as the same thing as the one we have on the left. We end up getting K to be Coulomb constant, 9 times 10 to 9 meter squared divided by Coulomb squared. And that's it. One important thing, both of these, electric potential energy and electric potential, again, are scalar. So negativity shows magnitude, not direction. They don't have a direction. Here, compare VA, VB of potentials due to charge Q. We'll just write them down. VA will be K, Q over RA. No squares. VB will be K, Q over RB. RA is 1, RB is 3 millimeters. I don't have to even convert the units as comparison. I'll say VB over VA should be 1 over 3 here, smaller. As the potential goes, as we go away from the charge, potential will decrease away. Assume our charge is here. And we imagine what we call equal potential surfaces around the charge. If I have a charge in the center, there are surfaces of equal potential around that charge, and we call them equal potential surfaces. This is 3D configuration of it. We can symbolize this as lines, dotted lines or circles around the charge. Those are all equal potential surfaces. So if this is V1, let's say, this is V2, all along the surface I always have the same potential, thus equal potential surfaces, V1 and V3 and so on. And electric field turns out to be always perpendicular to these surfaces or equal potential lines, everywhere perpendicular. That's the relation between an electric field and potential. Think about this question. We're going to solve it in another video. What is the electric potential of one centimeter from 1 nanocoulomb charge? What is the potential difference between a 0.1 centimeter away and a second 0.3 centimeter away? So I have a charge, it's positive, 1 nanocoulomb, 1 times 10 to minus 9 coulomb. What is the electric potential at here? Let's say R1, 1 centimeter. I'll call this V1. What is the electric potential here? Let me draw it a bit farther. It's 3 centimeters, so it should be a little bit farther. 3 centimeters away, let's say here, 3 centimeters, R2, V2. First, what is this potential? And the second question says, what is the potential difference in between? Which will be V2 minus V1. And our equation is V is equal to K Q over R. Simple as that. We'll solve this problem in another video. But have a look at it. It should be solvable easily. If I have more than one charges, what I do is calculate all the potentials and add them. Mind the negativity. If I have a negative potential, I add it as negative. Or positivity, right? Or positivity. So mind the charges. I know this equation is scary. We have sum of I, KQI over RI, but here's what it means. If I have two charges like in here, Q1, Q2, I call them. This QI and RI represents that. And let's say I'm trying to find what is the potential due to those over here at this point. Oh, let's say I'm going to find the distances R1 and R2. I'm going to calculate potential differences. Each will have a different one, V1 and V2. No direction, scalar, remember, and add them. I don't have to worry about directions. A very common mistake is to assume they are vectors, show directions, almost. Just add V there will be equal to V1 plus V2, but I have a negative charge here, so V2 will be negative. No absolute value here. We're going to put all charge, sign of the charge will give us a sign of a potential difference. So K Q1 over R1 plus K Q2 over R2. This is plus, Q1 is plus, so V1 is plus, positive. And this is negative because Q2 is negative. Find those, add them, you'll have your total. That's what this equation is overall telling us. I have a third charge, fourth charge, I keep adding, and so on. We'll solve some problems on that. This one is about two charges. I'm going to call these Q1 and Q2. And the question is telling me at which point or points the electric potential is 0. We will add, again, mind and the direction. If I call this charge Q, that's minus Q actually. This charge will be plus 2Q. Mind on the equations for V general equation, KQ over R. If I have twice the charge, I should look at twice distance away to have the same V. V1 and V2 should be equal to each other and opposite in sign, not direction. So V1 should be equal to minus V2. That's the idea here. For that to happen, twice the charge, twice the distance, I have to find points that are twice farther away from charge 1. If I call this R, I have 2R here, and this is one point here, point C. Works. On the left side, there's no way I can make it work because my point should be closer to the smaller charge. So left side is dropped. In the middle, I found C. B wouldn't work because it's closer to the larger charge. D also would work if I look at D. Let me call this D maybe, distance D. The distance to Q2 is D. In this sense, distance to Q1 would be 2D. This would be also a D distance. So D also works. Let me also add them here for C, for example. I'm going to have V total is equal to V1 plus V2. Let's put them in. K 2Q over 2R minus K. My charge is not minus here, so I directly put V2 as minus K Q over R. And these cancel, divide by 2, I'll have 0. The same way D also works. So, well, the answer is more than one of these, but C and D actually would be better. Nicer looking answer. Think about this question. We'll go back to it as well. I'm looking for total potential here. I'm going to call it V total. It's actually the same question turned around. I'm going to call this charge Q1, this charge Q2. Remember, no direction. This is actually easy. I don't have to worry about direction. I'm going to find them and add them. But this is my R2. I have to find that R2. This is my R1. And my answer is this. V total is equal to K Q1 over R1 plus K Q2 over R2. No direction, charge matters. No direction because V is scalar. Careful about that. Many of you calculations like Coulomb forces, electric fields shows direction. No. Potential is a scalar. V is a scalar. Don't forget. Just add them and it's simpler. And keep the sign of the charge. So potential can be positive, negative, or 0. But it's not plus direction or minus direction. Its value is scalar value is positive, 0, or negative. How does potential and electric field are related is actually a simple idea. As we talked in the previous lecture, potential and electric field is intrinsically related. If we have an electric field, we have a potential difference. Over here, I can assume I have plus parallel plate here, minus there, parallel plate capacitor. I have electric field plus the minus always. Let me try that again. Terrible job there. So there is a charge separation. There is electric field from plus to minus always. And if there's charge separation, there is also potential difference. Plus is generally high potential. Minus is generally low potential. So there is a delta V. This is very similar to gravitational. Closer to the ground we have low potential, and higher from the ground we have high potential. So high and low. And we have G downward. And we also learned in the previous lecture that positive charges moves from high to low potential, their kinetic energy increases downward, potential energy decreases, and opposite happens with negative charges. This is one kind of relation between E and potential. But there is a more subtle relation. I can draw what we call equipotential lines. So I can draw a line. Along that line, electric potential can be the same, like in this figure here. If we carry charges and we do a work is equal to Q delta V, remember, and that's equal to UE. So if I'm doing a work, I'm storing an energy in my charge, and that's the electric potential energy. If I'm not doing a work, I'm not storing any electric potential energy. And if there's no change, I'm carrying a charge and there's no change in delta V. If delta V is 0, my work is 0, so no change in potential energy. If there's no change in potential energy, you might remember from previous classes that if I move an object, move objects perpendicular to forces, no work is done. That means if I'm not doing any work, let's say I have this line over here, 10 volt, I carry a positive charge along that line, I do no work, no storing of electric potential energy. This tells me I'm moving this charge perpendicular to the electric force applied to this charge, QE, right? Remember? And remember also the force applied to a positive charge is along the same direction as electric field. So electric field is also perpendicular to here. This gives me this idea that electric field lines are always perpendicular to the potential lines. One more information from this page we want to get is that I can calculate electric field lines in between two potential lines by finding the potential difference and dividing it by the distance in between. So overall summarizing, if we have the drawn equipotential lines, what we call equipotential because it's again along a line, all the same potential. Electric field will always be perpendicular to those equipotential lines. Since I can calculate the electric field value using this potential difference divided by the distance in between, if there are equipotential lines closer, electric field will be larger. This large vector shows electric field is larger here. Let's call this actually E1, E2, E3 to clarify this more. And as the equipotential lines separates, we have smaller and smaller electric fields. So if I want to compare the electric fields here, I say E1 is larger than E2, larger than E3. As the equipotential line separates, we have smaller electric fields. Similar to as electric field lines separates more and more, we have smaller and smaller electric fields. In this picture here you see different charge configurations and their electric field and equipotential lines. Positive charge, these green lines are equipotential lines. At each of these lines we have equal potential. Let's call this V1. All along the line here I have V1, not changing. If I call the other one V2, all along this line equipotential, so potential is all equal. An electric field is perpendicular to those lines everywhere. This helps us draw electric field lines only knowing equipotential lines and vice versa. Electric dipole, we already talked about electric field and how to draw it and so on. Equipotential lines will be perpendicular to those everywhere. And this is for parallel plate capacitors. We already talked about electric field as well. Equal separation because we have the same electric field. Then we would draw the equipotential lines as these green lines here, and they will also be equally separated. A proton starts from a rest at point A. It then accelerates past point B. Proton's kinetic energy at point B is, starts from rest, the initial kinetic energy is 0. And here it will have a final kinetic energy. It's moving through this delta V. This is V initial, this is V final, right? So V final minus V initial minus. It's 150 minus 250, so 150 volt. That gives me a minus 100 volt. Let's put it here. What do I remember? Delta K is equal to minus Q delta V. Notice here that the energy is given in eV, so I'm going to take my Q is the Q of the proton, charge of the proton, and it's equal to E. I'm going to take it as E. Then I'm going to take volt as V, and I'm going to get the energy as EV. Now, K final minus K initial equals minus Q delta V. This dude was 0. This is my K final. Equals minus E times minus 100 volt. So K final should be 100 eV. I am moving one proton along with potential difference of 100 volt. Its energy change would be 100 eV. Same would be for electron, except electron should be going in the opposite direction to increase its kinetic energy. Remember, electrons like going from low to high potential, kinetic energy increases, and the opposite happens for the protons. They go from high to low potential and their kinetic energy increases. At the midpoint between these two equal but opposite charges, what is the electric field and what is the electric potential? Ooh, nice. Electric field, a vector. Let's show it first. Negative charge always towards, let me use blue for negative. Let's give them a name, Q1, Q2. E1 is towards my charge, and it's always away from positive charge. E2 is away. So both electric fields are in the same direction. When I add them overall, I'm gonna have E1 plus E2, or E total, let's call it, to the right. But potential, same distances. One charge is positive, one charge is negative. We will have V total is equal to V1 plus V2. As scalars, no direction, so we'll have K. Let's call these plus Q and minus Q. And when we put that minus, V2 will be minus. So we'll have K, Q over R, minus K, Q over R. 0. So potential is 0, but electric field is not, and it points to the right. This is also a nice question. It's asking about delta V as we move a charge from here, taking this path there. Delta V is always, that's the point here, V final minus V initial, no matter what path you take. These are all equal potential surfaces, so this is all minus 50 along. So V final is at F. V final is minus 50 volt, and V initial is 0. So delta V will be the difference here. Final minus initial minus 50 volt. And that's our answer. Another nice question here. Which set of equal potential surfaces matches this electric field? If you look at the vectors, electric field is a vector. It's to the left and it's increasing. So E is increasing as we move left in this direction. If E is increasing, remember the equation for E relating to equipotential surfaces or the electric potential, delta V over delta D, or D, the distance in between. I have equipotential surfaces for each option, starting at 0, increasing to 50, right? But they are not happening in equal steps. It's changing. The D in between is equal here. It's decreasing here. Let's call them D1, D2, and so on. It's increasing on C, if I call them D1, D2 as well. First of all, let's look at the direction. I have low potential on the left, high potential on the right. From A to C, we have the same situation. Electric field direction is always from high to low. That's one relation. And again, to remember this, always put plus charges on this side and minus charges on that side, and say electric field is always from plus to minus, and plus is always high, minus is always low potential. And electric field is to the left, high to low. If I have low on the left and high on the right, high on the left and low on the right, so I have high, low, I can cancel D because the electric field first of all will be to the right here, so that's not the case. The same here, if I apply an electric field, it will be to the right, that's also cancelled. Electric field is to the left for all of the rest, but it should be increasing. For it to increase, equipotential lines should be getting closer. And only C shows that equipotential line is getting closer and closer, smaller and smaller D. I'll say D is decreasing here. So electric field will increase, and that will give me my answer. This is my electric field here. This is equipotential line 0, 100, 200, finding the electric field here. I'll leave this to you, but you'll find that delta V and you'll find that delta D overall in the center. Delta D, or let's call this D. E is equal to delta V over D. So 200, right? This is 2 centimeters. 200 volt divided by 0.02 meters is your answer. How much is that? 1 times 10 to 4 volt per meter. We came to a point of seeing that this actually brings us another unit for electric field, volt per meter. It's equivalent to Newton per coulomb. Alright, so we learned something new. We learned that electric field is always perpendicular to the equipotential surface. We learned also before that for conductors, always pushes charges to the outside, to the surface, like this figure here, and electric field is 0 inside. We also knew that electric field is perpendicular to conductor surfaces everywhere. This tells us that conductor surfaces then should be equipotential surfaces, and they are equipotential surfaces. Electric field is always perpendicular to equipotential surfaces too. So that's one new information we learned from this section about conductors. We are all electric. We have electric charges stimulated, pushed around by nerves and muscles and so on. That's how our body works. And we talked about the polarization of the heart in an electric dipole. This part talks more about that, how this carried along the heart and always changed, having the electric field change in what we use in electrocardiography. Actually, change in electric field causes change in electric potential, and that's what we measure. As the heart works, these figures are showing how the potential different changes at different points in body and different time of the work of heart, and this figure is showing how we measure it and see its value with time. T is time here, and this is delta B, potential difference. And as they put these electrodes in our body, they measure the potential difference at those points. See you on the next lecture.